Welcome to the session on accelerating the internet edge. My name is Vijay Sivaraman. I'm a professor right here at UNSW Sydney, where we are currently. Oh, this one doesn't work well enough, or yeah, is that better? Okay, wonderful. So so we have 4 exciting talks here. So let's just get started. The first talk is being presented by Lei Yang, who has just finished his PhD a few months back from MIT, working with Professor Mohammad Alizadeh. His research focus has been on fault-tolerant distributed systems and the underlying networks. He seems to be very passionate about blockchains. In fact, he's the co-founder of MegaETH, which is a crypto blockchain startup where he's the CTO. So over to him to talk about practical rateless set reconciliation. Thank you.
All right, thanks so much for the introduction. Happy to be here to talk about how to kind of synchronize data sets with almost optimal communication and computation costs. So this is a joint work with Yossi from Hebrew University and my advisor, Mohammad Alizadeh. All right, so synchronization is a common primitive in distributed systems. You have tools like rsync, and it's essential in protocols like gossip protocols, and also it's becoming increasingly more important in peer-to-peer systems like blockchains. And there's a nice abstraction of synchronization, which is called set reconciliation. So imagine that you have Alice and Bob, 2 computers, and each of them holds a set of items, and each item is basically a fixed length bit string, right? And the items can be really anything, like file system blocks, database keys, DNS records, whatever, right? And their goal is to compute the symmetric difference between their sets. In other words, the items that are unique to only one of them, but not both, and we denote it as A delta B. So they want to do this because really, if you kind of know the symmetric difference, then you can push the items that the other end is missing to the other end, right? So the 2 sets are synchronized. Right, so there is a straightforward lower bound on the communication cost, which is the size of a symmetric difference. It's basically based on information theory, because that's the amount of data that you learn after the process. And in practice, there are straightforward solutions, like Alice can just send her entire set to Bob, and Bob can figure out what items Alice is missing and probably send it back. And you'll see that it's really inefficient, because it's sending the entire set of Alice set. And in practice, people do kind of optimize a bit by, say, sending hashes or sending Bloom filters of the of the sets instead of entire individual items. But it does not really change the asymptotic cost. It does not really change the asymptotic cost of the protocol, right? Because Bloom filters even does not change the kind of, it does not improve the cost asymptotically. All right, so a more optimized solution would be that you construct Merkle trees out of the sets. So a Merkle tree has a nice property that each internal node is the hash of its subtree. So basically, you can just compare 2 subtrees by comparing their roots. And Alice and Bob can compare the nodes one by one from the top to the bottom to figure out all the differing leaves. And they basically figure out what items are different across their sets. But it involves a large number of interactive rounds, and you take a logarithmic factor of communicational blow up, right? All right, so there is actually a very promising solution, which is called a linear sketch. So a linear sketch is basically a summary of a set, and under some conditions, you can kind of reverse the process. You can kind of decode a sketch and recover the original items covered by the sketch. And the nice property is linearity, which says that you can combine 2 sketches, say sketch of set A and sketch of set B, and the result will be the sketch of the symmetric difference, right? So now Alice can just send her sketch to Bob, and Bob will locally combine the 2 sketches using linearity. And Bob can then decode the resulting sketch to obtain the items in the symmetric difference. So I mentioned that you can kind of decode a sketch to obtain the original items under some conditions. So let's see how it works. A sketch is basically a collection of symbols, and each symbol is the sum of a few items. So imagine that this is the sketch that, this is the set that Bob tries to decode, the kind of the symmetric difference, and this is the sketch for the symmetric difference, okay? And each item is randomly mapped to one or a few symbols. And for example, here, item A is mapped to symbols 0 and 4, and so on and so forth. And each symbol is basically the sum of the items that are mapped to it. For example, here, symbol 0 is the sum of items A and E. And to decode a sketch, you use a process called peeling. And you start with something called a pure symbol. So a pure symbol is basically one that has only one item mapped to it. For example, symbol 2. And symbol 2 is basically the sum of, I cannot see it, but yeah, okay, of item D itself. So basically recover item D by looking at symbol 2. So you can now remove item D from the other symbols. It is mapped to like symbol 5, so symbol 5 becomes pure, and you repeat the process, and you kind of just do this recursively until you recover all the items, right? And I mentioned that you can only do this process successfully under some conditions. And the rule of thumb is basically that for you to successfully decode a sketch, the size of the sketch or the number of symbols it contains has to be at least twice as many as the number of items. And it's kind of a mathematical result, but the intuition is basically that if you are really unlucky, because if you have, say, too few symbols, then you may end up at this situation where you don't have a pure symbol to start the peeling process. Or it can be that you run out of pure symbols in the middle of the peeling process. So what we see here is that traditional sketches, they are inflexible in the sense that there is a design capacity that is fixed during the construction of the sketch. And the thing here is that in reconciliation, you don't really know how many items are going to be in the symmetric difference, because otherwise you already know the symmetric difference. So for example, if the actual number of items is smaller than the capacity, then you waste a lot of capacity, and in other words, you waste communication. And if the actual number of different items is larger than the capacity, then you'll fail the entire process. And yes, existing protocols, they kind of mitigate this problem by using online estimations, but this kind of result is fuzzy, and it creates its own problems. So what would be really nice is that if we could design something called a universal sketch. So a universal sketch should have an infinite number of symbols. So it has an potentially infinite capacity to accommodate an infinitely large set difference. But importantly, every single prefix of this infinite sequence of symbols should also be a sketch whose capacity should be linear to the length of the prefix, right? So the way that you can use this is you can say require Alice to generate symbols in this infinite sequence for her set one by one, and send the symbol to Bob. And Bob will locally combine the symbols using linearity, and then Bob gets a symbol for the symmetric difference. And as Alice sends more and more, and Bob combines more and more, the kind of the prefix that Bob has will grow, and then the capacity also grows. And when the capacity exceeds the number of differences, Bob can decode, and Bob can then tell Alice to stop, because he's kind of finished with the process. So we actually went to design such a system, and it's called Rateless Invertible Bloom Lookup Tables, or Rateless IBLTs. And to reconcile D differences across two sets using Rateless IBLTs, you need on average 1.35 to 1.58 D symbols, where the actual coefficient depends on D. And it's computationally efficient. To generate D symbols, you have to scan the set log D times, and also it's similarly efficient to decode. All right, so I'll quickly discuss how we designed Rateless IBLTs. Our design space is really to kind of define this mapping rule, right? For a given item, how should I map it to the symbols? I should kind of generate a sequence of indexes, an infinite sequence of indexes that item A should be mapped to. And I define this rule for any kind of bit string, then I basically have the sketch defined for any set, right? So importantly, we want it to be decodable without requiring too many symbols. In particular, we want the number of symbols that you need to finish decoding to be linear to the number of differences you are trying to reconcile. Then we're basically very close to the information theoretical lower bound. All right, so this problem sounds a bit abstract. So let's try to constrain our design space, right? So we can try to kind of infer or try to guess what properties we want from this kind of mapping rules. And in particular, we can focus on this kind of property, which we call the mapping probability. It basically defines, we define it as kind of the probability of mapping a random item to the ith symbol. So we call this the mapping probability of the ith symbol, or denoted as rho I. And we can then kind of try to do some analysis on what properties we want out of this function rho I, such that we can ensure efficient decoding. And I'll skip the math here, but basically we showed in the paper that this function rho I has to be inversely proportional to I, at least asymptotically. So what we actually did was that we showed the converse, right? So we showed that if rho I is either larger or smaller than 1 over I asymptotically, then you cannot decode with a linear overhead, with a linear cost. The overhead shoots to infinity as the size of difference increases. And to give you some intuitions, for example, here, if rho I decreases too slowly, the graph is too dense, and you don't have enough pure symbols to sustain the decoding process. Or if rho I decreases too fast, then the graph is too sparse, and you waste a lot of space on these empty symbols, which does not really contribute to decoding. So when rho I is 1 over I, you get a nice balance, because it's sparse enough so that you keep getting pure symbols in the process, and it's not too sparse so that you don't waste too much space on empty symbols. But you will see that, hey, I only talk about the necessary conditions, in the sense that rho I cannot be something that is not 1 over I asymptotically, but we didn't really show that 1 over I works. So we used density evolution, which is a classical technique in analyzing LDPC codes or LT codes. And we kind of tried to analyze rho I in this format. So we added a coefficient alpha, and we shifted the denominator by 1, because in our notation, I starts at 0. And so this analysis will tell you what is the overhead as the difference size goes to infinity. So it basically says that the overhead should satisfy this condition, and we can plot it. And this is the result. It's the relationship between the parameter alpha and the overhead. So in the end, we picked alpha equal to 0.5 due to some practical reasons, and we got a overhead of 1.35, and that's the number you heard in the previous part of the talk. And for finite size of differences, you can run Monte Carlo simulations, and you can see that the overhead converges quickly to 1.35, as predicted by density evolution. And you can also get the decoding process from density evolution, basically saying, given how many symbols Bob has received, what's the fraction of items that he can decode? And you can see that the simulation matches really well with the analysis. And probably last piece is, how can we actually design an algorithm that concretely decides for any item X which symbols it should be mapped to, right? And again, we want it such that for random X, it's mapped to the ith symbol with probability rho I, as we just mentioned. So the very straightforward solution would be that you flip a coin for every pair of X and I, and it goes head with probability rho I, and that's how you guarantee that you kind of make the connection with probability rho I, right? But the problem here is that it's not very efficient, because suppose that you have mapped item X to symbol I, and you want to decide what is the next symbol that X should be mapped to. You have to keep flipping coins, and actually OI number of times until you hit the next mapped symbol. So it's not very efficient. But on the other hand, you can just try to sample the distance between two consecutively mapped symbols directly, this random variable delta. And turns out that by some magic, there's a very nice closed form approximation of its cumulative mass function. And there's also a very nice approximation of its inverse. So what you can do is just sample a random number uniformly from 0 to 1, plug it into the inverse of the CMF, you get delta, and then you get j equal to I plus delta in a constant time. So to quickly recap how you use this, Alice will send this symbol stream to Bob, and Bob will get an increasing long prefix of the rateless IBLT of A delta B, and at some point he can decode and tell Alice to stop. And we call it rateless IBLT really because we're kind of inspired by this family of research called rateless codes and digital fountains. That is for erasure channels, but our code is basically a family of rateless codes for set differences. And the symbol streams are universal in the sense that you can use, Alice can use the same stream of symbols for reconciling with different peers holding different sets. And if Alice decides to kind of cache a few symbols, then later if she modifies the set, she can also efficiently update the cached symbols. All right, so we did an implementation in 400 lines of Go, not using any third-party libraries. And users to use the library needs to define how to hash and how to add two symbols. There are also third-party open source implementations. And for experiments, we focused on two things. One is a micro benchmark comparing rateless IBLTs with other solutions. And the second is an end-to-end experiment synchronizing Ethereum account states. So I'll focus on the second experiment. So we basically set up two clients, one holding the latest state of Ethereum blockchain, and the other holding a slightly outdated version with a variable staleness. And we kind of simulate a kind of an internet connection between the two clients using Dominet in in FreeBSD. And as you increase the staleness, there's more data to synchronize, right? So of course, the time and the communication cost increases, but rateless IBLT outperforms the production system, which uses Merkle choice by at least a factor of 4 across the entire range. All right, so to recap, we designed rateless IBLTs. It's very efficient in terms of communication and computation, and the efficiency is really anchored by rigorous proofs. And this ratelessness property makes it very easy to deploy, no need to estimate the size of the difference, and the same stream of symbols works for any number of peers that you want to synchronize with. And with that, I'm happy to take questions.
You blew everyone away with your mathematical work. So, questions? Maybe I'll give it a try. What might be the most immediate application of this for the networking community?
So one application we considered but did not end up kind of running was RPKI, because it basically involves synchronizing sets of like public keys and records. So basically, whenever you want to kind of synchronize sets of small records, it works really well when you have small items, because otherwise probably sending the hash will kind of be fine, probably. But when you have kind of small items, large sets, and also small changes across two copies, it really shines.
Any other questions? Well, if not, let's thank the speaker. And